Well, all right. I guess we can go ahead and get started. Let me just get this set up here. Um, okay, sorry. I need to code switch here for just a second. Okay, yeah, so a little bit of housekeeping before we get started. So my apologies there. Somebody made me aware that there was a CSV file that I should have included in assignment 3 that I forgot to. So if you haven't seen that email, again, the seeds modified CSV file that you need for the Jupyter notebook part of assignment 3 that is now posted on Canvas, where you initially downloaded that zip file. So that's there. Also, do keep in mind, as we are going to be doing every Tuesday, we will have our checking Tuesday. So I have set up I'm trying to get this to work here. So I have set up the emails to go out at 4:30. And again, I think the key thing that I want to emphasize here is, like relax. This is not like some heavy-handed thing here. I'm not necessarily checking to make sure that you are getting the right answer, but just more that you have some sort of thought process that you can articulate for a given answer. And again, the question that you will, be seeing will look very similar to something that you saw or that you submitted in your, previous homework assignment that you just submitted. So again, the best way to really prepare for checking Tuesday is to, basically just make sure that, whatever you put down on your homework assignment, you put some thought into it. You didn't just kind of write an answer down without really thinking about the why or the logic behind that answer. So yeah, I've randomly selected 12 people. So at 4:30, I will take about a 30-second pause for everybody to check their emails. And again, if you've been selected, what you should do is log off the Zoom meeting and record your less than 10-minute video and submit it before 4:50 in order to get full credit. Also, do make sure that when you are creating your recording that your mic is on, your camera's on, and you're sharing your full screen so we can see what you're doing essentially. So anyone who doesn't meet all those specifications will lose points. So do make sure you remember all the things that you're supposed to do. And then, we have our next homework assignment that is due this Friday with office hours as always. And I think that's basically it. Any questions related to housekeeping? Okay. All right, cool. And so what we're going to do today is we wrapped up with Unit 4 last week, talking about how we can use TS&E plots and the TS&E algorithm to learn more about the clustering structure that exists within a given data set, and to also help build corroborating evidence when it comes to essentially evaluating whether our actual clustering algorithms are really identifying the types of clusters that we're essentially looking for. So again, the key thing that we want to remember is that the TS&E algorithm is not actually a clustering algorithm. It should not be used as such. It's a dimensionality reduction algorithm that preserves some aspects of the clustering structure. And it essentially should be used as an aid to help build corroborating evidence that the clusters that you found with actual clustering algorithms, like k-means, are in fact meaningful. Or in other words, for instance, we're not simply just taking a blob of points and cutting it up into 2 with k-means. The TS&E plot can actually give us evidence to suggest whether those blobs of points or those clusters that we're finding with k-means are in fact actually separated from each other. So here's a warm-up that I gave. And basically in Unit 5, we're going to be moving back to a clustering, an actual clustering algorithm. So Unit 5 is going to be all about how to use hierarchical clustering algorithms to answer various clustering related questions about a given data set. And so this is the data set that we're going to be exploring in this unit. So we have all of the countries and 9 numerical attributes regarding each of those countries here. And essentially what we'd like to do is create sensible clusters of countries that have essentially not just one observation. So basically one of the stipulations of our, let's just say, research motivation is that we don't want any clusters of countries to be basically just like one observation by itself. We want to be able to extract meaning from these clusters. We want to, put them into buckets that we might, for instance, make decisions on based on what bucket they belong to. So one such, motivation that people use this type of analysis for is, for instance, like climate, international climate change negotiations. So quite often, in those negotiations, countries get placed into different buckets, and those buckets essentially dictate, what types of interventions these countries should make, when it comes to, mitigating greenhouse gases, essentially. So cluster analysis is one such way that we might go about doing that. And so therefore, a motivation such as that, it doesn't really make sense to have a single observation by itself. So that's going to be one of the stipulations or one of our particular research goals when it comes to selecting the best clustering of this data set here. So keep that in mind. But what we want to think about is, so basically we've taken this 9-dimensional numerical data set and we've put it into a carefully selected t-SNE plot with perplexity value 30 in a particular random state. So now let's just assume that, let's make this assumption here. So assume that you see this structure across multiple random states and perplexity values. That's it. So basically assume that this is not just a fluke that we're seeing here, or something that was just due to a particular perplexity value. So the warm-up here is basically evaluate whether or not you're able to make each of the following interpretations about the original data set. So I'll give you guys maybe about 10 more seconds to select all of the statements that you think are true. Okay. I'm usually a person who's like very awkward when it comes to like dead air time in Zoom meetings. This is actually pretty good for me here. Okay. All right, so I'm going to end the poll in the next 5 seconds. Okay. All right, so let's share what we put. Okay, so the first interpretation that we might make based on this t-SNE plot, which we can assume looks very similar to other t-SNE plots that we've seen, is one in which we might interpret that there's 3 main clusters, and that some of these clusters could be further broken down into subclusters. So yeah, that is something that we can in fact see based on this plot here. So for instance, we might see that, we see some separation here. So this might be a cluster. We can see mostly some separation here. So this might be a cluster, and this might be a cluster here as well. And furthermore, we can see, for instance, this cluster does have some additional gaps that show up. So it's possible that, this could be evidence that, for instance, this cluster here could further be broken down into some clusters. So I'm seeing 3, main larger clusters based on what I see. And so the second interpretation might be one in which some of the clusters are not well separated. So it looks like most of us said that, yes, that is the case. And so, yeah, we do see that these 2 clusters in particular do not look very well separated. So that could be an indication that, yeah, these 2 clusters that exist in the higher dimensional data are also perhaps not well separated. So we're also seeing this potential interpretation that not all 3 of these main clusters are of the same size. And so, for instance, we see that this cluster represented in the middle does in fact have, more observations assigned to it. We can see that, for instance, this The three main clusters are convex in shape. So, yeah, I mean, it really kind of depends on your interpretation here. Like, what did you choose to represent as a cluster? So it's possible that, for instance, this cluster here, this might be non-convex. Because, for instance, if this was the shape of the cluster as I've drawn it like this, there are in fact 2 points in the cluster that don't actually end up in the full shape. So, for instance, like, if I had drawn that shape a little bit more tightly around the points here, we can see that basically this line that we draw between points within that cluster does leave the shape. So we might actually, in fact, say that, for instance, one of these clusters is non-convex. One of the main clusters may be interpreted as non-convex, but it depends. So for instance, you might have interpreted, this as a cluster, this is a cluster, and this is a cluster. And if that's the case, this cluster here in the middle is beginning to look a little bit less, non-convex. Cool. Oh my God, that's amazing. Everybody got it right for number 5. Yeah, I love that. So number 5 is claiming that based on what we see here, this data set has no outliers. And yeah, so we cannot make that interpretation based on a TSNE plot. So you want to recall, TSNE plots do not indicate whether or not your data set has outliers. So in fact, something that we're going to find or see in the analysis is that this country here, for instance, Nigeria, is in fact a very far away outlier from the rest of the points in the data set, in the actual data set. But in the TSNE plot, it was lumped in with basically its closest set of observations, because again, what the TSNE algorithm is attempting to do is to preserve the nearest neighbor relationships from the highest dimension or from the high dimensional data set. And so basically the perplexity value, again, is our number of nearby neighbors that we're assuming that every observation has. So basically, if we set our perplexity value to be the lowest value of the lowest value that's actually useful, 5, what that means is that Nigeria is going to be forced to have at least 5 nearby neighbor countries in the TSNE plot. So therefore, we're unable to see that Nigeria is in fact an outlier. Okay. So also, we are not able to determine sparsity from clusters. So we want to keep that in mind as well. So TSNE plots do not reflect cluster sparsity, given that pairwise object distances are not preserved in the projection. Okay. And the final misinterpretation that we might make is that, for instance, this pink cluster is about as equally far away from the yellow cluster as it is from this green cluster here. And so, what we can see in the TSNE plot is, for the most part, this yellow cluster looks about the same distance away from the pink cluster as the green cluster looks away from the pink cluster. But for all we know, this yellow cluster could in fact be a lot further away from these clusters here. So again, this is not an interpretation that we can faithfully make. But TSNE plots do not preserve the distance, or the distances between clusters. Okay. All right. So I really like to hone the interpretations of TSNE plots in class, because this is one of the most common things that I take off points for in the final project. So just keep that in mind. Okay. Any questions on that? Okay. Now, given the fact that we do in fact have some sort of a suggestion that there could be a subcluster cluster relationship, particularly like, for instance, in this cluster here, that indicates to us that a hierarchical clustering algorithm might in fact be useful. Because as we saw, a hierarchical clustering algorithm will return not just a single partition-based clustering of the data set, but it actually in fact returns a series of nested clusterings of the data set. And so in addition, an additional follow-up question that we might have about even just a single clustering, right, is, well, how far away are each of those clusters from each other? And so we discussed that we can't determine this from a TS&E plot, but this is in fact something that we can determine from a carefully chosen dendrogram. So for instance, what this dendrogram is showing us is that the final two clusters of countries created in this data set, basically the final two clusters to be merged in this particular algorithm that created this data set, is the one that contains these countries here and these countries here. And then basically we create this, if we go down the line, we wanted to create a clustering with 3 clusters. And we could draw this vertical line here. And what that reflects is a clustering with 3 clusters. And so what that shows us is basically this clustering of countries here further broke down into these 2 sets of clusters here. So basically what that tells us is that the most, of these 3 clusters, the most distinct set of countries are these ones here. And then basically the second most distinct set of countries are these ones here. Or in other words, basically these 2 clusters of countries are closer to each other than, for instance, these 2 clusters of countries. So that might be relevant information that, let's just say, climate change, international negotiating bodies might want to know, based on how they want to use that information. Okay, so these are all things that a hierarchical clustering algorithm can tell us. Yeah, so basically that's what we're going to be exploring in this class here today. So, like I mentioned, just to kind of recap where we were at. So hierarchical clustering algorithms allow for us to display a series of nested clusterings graphically displayed in a dendrogram. Okay. And so we've kind of already discussed how to interpret a dendrogram in previous units. But again, if you ever want to extract the clustering reflected in a given level of a dendrogram, again, what you do is you draw a line that intersects the tree and you follow it down to each of the resulting observations reflected at the bottom of the tree. And then what that does is it creates a resulting clustering of the data set here. Okay, there's actually, okay, so I've been doing a lot of talking. Any questions before I move on? Okay, so there's actually 2 main types of hierarchical clustering algorithms. So the 2 main types are agglomerative versus divisive hierarchical clustering algorithms. And the main distinction is basically the order in which they create each of these nested clusterings. So we say that an agglomerative hierarchical clustering algorithm starts with all objects apart in singleton, what we call singleton clusters. Okay, that would be something like this. And then it iteratively joins clusters or 2 clusters together until all objects are together in the same cluster. So for instance, we might join 1 and 2. Then next we might join 3 and 4. Then we might join 1, 2, and 3, 4. And then we might join all of these together. So agglomerative hierarchical clustering goes in this direction. And by contrast, so basically an agglomerative clustering algorithm, it agglomerates, it puts things together. And so by contrast, a divisive hierarchical clustering algorithm starts with all objects together in a single mega cluster, if you will, and it iteratively divides clusters until all objects are apart in singleton clusters. Okay, so a divisive hierarchical clustering algorithm moves in the opposite direction. Okay, so today we're going to go through 4 of the most common types of agglomerative hierarchical clustering algorithms. And then basically on Thursday, we'll go through one of the most common divisive hierarchical clustering algorithms. But any questions on that? Okay, so this is the general way in which an agglomerative hierarchical clustering algorithm works. But now we're going to get more into a slightly more sussed out template for how an agglomerative hierarchical clustering algorithm works. So basically, this algorithm or this type of algorithm tends to have 3 main steps. As I'm describing each of these steps, try to think about what's vague about how I'm stating these steps. Okay, so the first step is to simply just create an initial proximity matrix of clusters. And the way that we do that is simply by creating a proximity matrix of all pairs of objects to each other. So again, you want to remember each observation starts out as its own singleton cluster. So basically the observations are in fact the clusters. So what's vague about this step here? Or what follow-up questions might you have for me? Yeah, exactly. So we might ask ourselves, how do we measure proximity, or for instance, similarity between 2 sets of, or 2 objects, i.e. initial clusters, in a data set? So for instance, unless you have reason to believe otherwise, perhaps Euclidean distance could be one such option. Okay. So whatever proximity measure you use to measure the distance between 2 objects, the next iterative steps in a hierarchical agglomerative clustering algorithm are the following. So next, what we do is we merge the clusters that are listed in the current proximity matrix. Merge the 2 clusters that are closest to each other. So basically merge the 2 observation or clusters that have the smallest current proximity. So something like this. And then what we do is we update the proximity matrix to reflect the proximity, not between 2 observations, but between 2 clusters. So basically we want to merge the 2 clusters that were merged. And let's just say it was 3 and 4. And so then we would need to create a new proximity matrix that looks like this. So what is vague about this step? In particular, the way in which we update the proximity between these sets of clusters here. What might we want to ask ourselves? So in this step, we were asking ourselves, how do we want to measure the distance between 2 objects? In this step, we'd be asking a slightly different question. We'd want to ask ourselves, how do we measure the proximity, i.e. similarity, between two clusters in this data set. So there's a variety of different ways that we could measure the distance between two clusters. And that basically the answers to this question dictate the different types of hierarchical agglomerative clustering algorithms that exist out there. So basically, the way that we measure the proximity between two clusters is what we call the linkage function. There's a variety of different linkage functions that you could use. One of them is called single linkage. One is called complete linkage. And one is called average linkage. And one is called Ward's linkage. So these are the most common ways to measure the proximity between two clusters. Okay. And so basically we merge each iteration of the algorithm, always merging two of the closest sets of clusters together until one cluster remains. Okay. Any questions on that? Okay. So we're going to come back to divisive hierarchical clustering on Thursday, but again, four of the most common hierarchical agglomerative clustering algorithms that exist are going to be based on the way that we measure the distance or the proximity between two clusters. Okay, so let's first focus on the single linkage function, or in other words, this particular way of measuring the distance between two clusters. And we're going to talk about why we would want to use this particular distance metric between two clusters. So, for instance, actually, I think I'm going to open up a breakout room. So let's talk about this in the breakout room. So we have this data set that we've seen before here. So we have the two clusters that we'd ideally like to detect. So we have, one spiral, and then we have the other spiral. So these are the two inherent clusters that exist in the data set. And ideally, we'd like for our clustering algorithm that we use to be able to identify these two sets of points as separate or existing in two distinct clusters. So basically what this means for a hierarchical agglomerative clustering algorithm is we want to come up with a distance metric between two clusters that will meet the following property. So we want to come up with a distance metric such that the red cluster is considered to be closer to the orange cluster than the red cluster is to this green cluster that we've identified here. So we can ignore all other points, but basically let's just assume that we're at a particular point in our hierarchical agglomerative clustering algorithm. And ideally what we'd like to happen in the next step is for the red cluster to merge with the orange cluster, as opposed to, because they're closest, as opposed to the red cluster merging with the green cluster. Okay, so I'm going to quickly open up a breakout room. Let's discuss this for the next few minutes, and then we'll meet back and discuss. Okay. Okay, so I've just opened up the rooms. You can change it if you'd like, but we'll meet back and discuss in a few minutes. Oh, shit. Sorry. Okay, so welcome back. Give people a few more seconds to come back to the main room. But yeah, curious to see what you guys came up with. So, what is a way to measure the distance between two clusters such that the distance between the red and the orange cluster is smaller than the distance between the red and the green cluster? Connection of dots. Um, well, so technically, based on the yeah, okay, so I see what you're saying. Yeah, so basically, can you connect this cluster to this cluster based on other observations in the data sets, essentially? Yeah, so you could do it that way. Now, let's just say, for instance, we didn't actually want to have to think about, whether or not a set of observations were connected or not. So there's another way that's a little bit more straightforward, I guess you could say. Yeah, so I'm seeing the max of the min points. Yeah, okay. So let's think about this way to define the distance between two clusters. So let's just say we choose to define the distance between two clusters as the proximity or distance between the two closest points in the two clusters. So if we define cluster proximity or distance that way, you can see that the red and the orange cluster have a distance of this, whereas the red and the green cluster have a distance of this. So therefore, if these are, two potential clusters in a given iteration of the hierarchical agglomerative clustering algorithm, what that means is that the red and the orange are going to join because they're considered closer than the red and the green. So this is basically what we want here. So the nice thing about using a hierarchical agglomerative clustering algorithm that uses single linkage to define the distance between two clusters is that it is actually the first algorithm that we've discussed that actually allows for us to identify non-convex, or excuse me, non-convex clusters as we're seeing here. So that's one cool thing about it. Okay, so let's actually cluster a small data set using hierarchical agglomerative clustering algorithm, specifically with single linkage as the way to measure the distance between two clusters here. And so let's just say, for instance, we'd like to, so basically we'll start off as we do any hierarchical agglomerative clustering algorithm by creating our proximity matrix of each of the clusters, i.e. each of the observations in singleton clusters. And for ease, we'll just use the Euclidean distance. So this is basically a Euclidean distance matrix for each of the observations here. Okay, so the first step, or the first iteration of the algorithm says we look at our current proximity matrix of the clusters, and we merge the two closest clusters based on this proximity matrix. So what two clusters would be merged in this first step here? So basically, what two clusters, based on what we're seeing here, are considered closest? I'll give you a hint. There's actually two potential answers you could give. Yeah, exactly. So you could have either gone with object 3 and 4 or 1 and 2, as they have the two smallest distances in this cluster. So in this scenario, you can, articulate some sort of tiebreaker rule. So for instance, let's just say in the event of a tie in which you could technically merge multiple sets of clusters, let's just say I've set this tiebreaker to be one in which you choose the pair, you choose the pair that has the highest index, for instance. So that's observation 4. So might choose to merge 3 and 4 first. So I'm going to merge clusters 3 and 4. And now what ends up happening is something that we also want to be keeping track of for when we actually create our final dendrogram is not just when two sets of clusters merge, but also the proximity with which they merge, or in other words, the distance between those two clusters when they have been chosen to merge. So basically the distance between 3 and 4 is 1.12. So we say that we merge clusters 3 and 4 at proximity 1.12. Okay. So I'll keep that here. All right. And so the next part of the given iteration of the algorithm is to update the proximity matrix accordingly. So now our current set of clusters are cluster 0, cluster 1, cluster 2, and cluster 3, 4. Okay. And so what we need to figure out is the distance between each of these new sets of clusters. Now, most of these distances don't actually require that much effort on our part to recalculate. So basically, the distance between cluster 0 and cluster 1, that's exactly the same. It's still just the distance between each of those points individually. So a lot of this we can simply just rewrite. So the distance between cluster 0 and cluster 2, that's still 4.27. The distance between cluster 1 and cluster 2, that's still 1.12. Now, what we actually need to figure out now is what is the distance between cluster 3, 4 and 1, cluster 3, 4 and 2, and cluster 3, 4 and 0. So this is where the single linkage function in particular is going to come into play. So what we said is the way that we measure the distance between two clusters under this linkage function is the distance between the two closest points. So what we can see is that 0 and 3 are the two closest points in these two clusters here. So therefore, and basically they have a distance of 4.03. So therefore the distance between cluster 0 and 3, 4 is going to be that 4.03. Okay. And next we want to find the distance between cluster 1 and cluster 3, 4. Okay. And so what we can see is that 1 and 3 are the two closest points in these two clusters, the distance of 3.91. So the distance between cluster 1 and cluster 3, 4 is 3.91. Okay. And finally, the distance between cluster 2 and cluster 3, 4 is going to be the distance between the two closest points. So we can see that observation 2 and observation 3 are the two closest points in these two clusters with a distance of 2.83. So therefore, the distance between cluster 2 and cluster 3, 4 is 2.83. Okay, so basically that concludes our first iteration of the algorithm in which we have clustered or merged two clusters together, and we have updated the corresponding proximity matrix of clusters. Okay, questions on that? Okay, so we move on to the next iteration of the algorithm where we use this new proximity matrix of clusters to choose to merge the two closest clusters together. So in this step, what two clusters are going to merge? Yep. So now we're getting around to 1 and 2. So we look up this new proximity matrix and we see that observation 1 and 2 are in fact the closest, or excuse me, cluster 1 and cluster 2 are the closest to each other. So therefore, in the next step, we are going to merge clusters 1 and 2 at proximity. That is the value or the distance between those two clusters. So also 1.12. Okay. So 1 and 2 are now going to merge. Okay. And so the next step is to update our proximity matrix accordingly. So now we have cluster 0, cluster 1, 2, and cluster 3, 4. Okay. So some of this stuff can be repeated. So cluster 0 and cluster 3, 4, we've already calculated that proximity above. So that was 4.03. But what we need to calculate now is the distance between cluster 0 and cluster 1, 2, and cluster 1, 2, and cluster 3, 4. So we're going to use that single linkage function again to measure the distance between two clusters. So if we want to find the distance between cluster 0 and cluster 1, 2, what we're going to do is find the distance between the two closest points in those two clusters. So we see that 0 and 2 are the two closest points with a proximity or distance of 4.27. So that would be the distance between those two clusters. And to find the distance between cluster 1, 2 and cluster 3, 4, we would find the distance between the two closest points in these two clusters here. So that would be 2 and 3, which have a distance of 2.83. So the distance between 1, 2 and 3, 4 is 2.83. Okay. That completes the second iteration of the algorithm. Any questions on that? Okay. All right, so now we have a clustering with 3 clusters. So we next need to examine this new proximity matrix of clusters and determine what are the 2 closest clusters that we would like to merge next. So what 2 clusters will be merged in this step? Yep, exactly. So we can see that 1, 2, and 3, 4 have the closest distance in the proximity matrix. So we would merge clusters 1, 2, and 3, 4 at proximity 2.83. Okay. And so merge those 2 clusters together. So now we have just 2 clusters left. And so the next step is to re-update our proximity matrix. We have 0, and then 1, 2, 3, 4. Okay. And so final step is to determine what is the distance between cluster 0 and cluster 1, 2, 3, 4. Okay. And so using the single linkage function to measure the distance between 2 clusters, we see that observation 0 and observation 3 are the 2 closest points in these 2 clusters with a distance of 4.03. So therefore, the distance between those two clusters is 4.03. Okay. So that concludes the second to last iteration of the algorithm. Okay. And so because we only have two clusters left, the final step of the algorithm is to merge those two clusters. So cluster 0 and cluster 1, 2, 3, 4 merge together. At the proximity between them, which is 4.03. Oh, okay. All right, so that concludes the algorithm. We're going to take this information and use that to construct our final dendrogram. But any questions on anything I've done so far? Okay. All right, so we're going to take this information and use it to create our dendrogram. So let me set up my, goodness, X and Y axis. Come on. Do that again. Okay, so what I set up on the y-axis of my dendrogram tree is the proximity with which a set of clusters are going to merge. And then on the x-axis is going to be the sets of observations in the data set. I'll put those here. Okay. And so what we're going to do is merge each of those sets of clusters that we merge in the algorithm at the corresponding proximity level. So 3 and 4 are going to merge at a proximity of 1.12. And similarly, 1 and 2 are also going to merge at that same proximity of 1.12. This is not drawn to scale. Do a little bit better. Okay, and then 1, 2, 3, 4 are going to merge at a proximity of 2.83. So we'll merge around this height here. And this is a little sloppy, but we're trying to draw this to scale here. And then finally, cluster 0 and cluster 1, 2, 3, 4 are going to merge at a proximity of 4.03. All right. And so what we've just created is a single linkage dendrogram. Okay, whew. We did it. Any questions on that? Okay, now the key thing here that you want to focus on in how we are constructing the dendrogram or running this algorithm for the single linkage function in particular is how we are reconstructing these proximity matrices. So when we move on to complete linkage, we're going to reconstruct these proximity matrices in a slightly different way. Okay, so now let's think about some of the types of data sets that we would expect single linkage to perform well on, and the types of data sets that we would think, or we would expect single linkage to not perform as well on. So let me ask you a poll here. So we have this data set here. Launch this poll. And so the question is, will hierarchical clustering, specifically when we're using single linkage, will it perform well for this data set? Or in other words, we can see here with our eyes, right, that there's two main clusters that ideally we would like to exist, or two main sets of points that we would like to exist in two separate clusters. All these observations together in one cluster and all these observations together in this cluster. So the question is, do we think that the single linkage dendrogram will ever be able to give us a clustering that meets all those specifications. So yes or no? And then if not, start typing up why we think not. Give it a few more seconds. Right. Okay, so most of us think no. So why do we think that? What's what's going to be the problem here? So let's refer to what we ideally might want to see in our dendrogram. So ideally, you know, this is what our dendrogram will look like for this data set here, right? We're like each of our observations in one cloud merge very early on with each other. Same thing for the observations in the second cloud. And then basically the final two sets of clusters to merge are, in fact, those two observations here. So this is what we would want. If we got a dendrogram like this, then basically we could say we identified the two main clusters. But what I'm seeing here is that, yeah, someone's saying like there might be one observation which is equally distanced between two clusters. Yeah, there's points that are very close together in opposite clusters, which will cloud the distance measurements. So the problem here is, we can see that these two main clusters that we'd like to identify, they're not well separated. So we'll start off with that. We'll say this first. So, the clusters are not well separated. So that's one contributing problem. And another contributing problem is basically, we can see this here. So there exists a denser bridge of points that connect them. So we want to remember, the sets of points, by using single linkage, basically what's going to end up happening is a observation or a set of clusters will link up to the closest cluster to them based on the two closest points. We can see that basically because these points here in the bridge are all very, comparatively closer to each other than the clusters or the observations in the main cluster, these are going to be the points that link up first. So they're going to basically link up in this connected path of very close points. And so basically, some of the first few merged clusters or sets of observations are going to be those in the bridge here. So they're going to look something like this in the dendrogram. And then basically, we've already kind of, merged sets of observations here with sets of observations here. So basically, what's going to end up happening as the algorithm progresses is that, we're going to basically expand the bridge to basically suck up observations on both sides. And so the bullet point is, maybe some observations will link up here early on with each other, within the cluster like this. And then the same thing might happen here like this. The thing is, these points are a lot further away from each other. So, these are going to happen here. And so basically, this merging between the two sets of clusters is going to happen very early on. So your dendrogram is going to, this bridging is going to happen, at very low proximity levels. And so unfortunately, what kind of dendrogram you're going to end up getting is something like this, in which we are unable to really visually see the separation that exists between the two main clusters that ideally we're trying to separate. So unfortunately, in a situation like this, hierarchical agglomerative clustering with single linkage will never yield a clustering with the two main clusters completely separate. as shown to the right. Okay, so this illustrates one of the downsides of using single linkage hierarchical agglomerative clustering, in that it's not as, or tends to be not as effective at identifying larger, what we might call main clusters that exist that are not well separated. Now, in addition, another downside to single linkage hierarchical agglomerative clustering is that it is sensitive to noise and outliers. Now, the term sensitive to noise and outliers, it's a very context dependent definition of a given algorithm. So we want to ask ourselves, what does it mean for a given algorithm to be sensitive to noise and outliers? So in the context of this particular algorithm, what that means is that it will identify, basically pick out outliers and noise at the expense of not being able to identify the, any main clusters, any larger main clusters that might exist. Okay. On the other hand, I'm going to skip to a benefit. If that's your goal, if your goal is to be able to identify outliers that you may not have been able to see in just a single two-dimensional scatter plot, well, that's cool. You can learn more insights about the outliers, which is very important, especially when it comes to selecting, whether your given clustering algorithm is appropriate, like K-means. So one benefit is that it can help identify outliers and noise that you, for instance, might not have been able to see in just a two-dimensional scatter plot. Okay. And then an additional benefit, like we saw, so basically this is our first algorithm that we've seen that is in fact able to identify those spiral clusters. So in general, it has this benefit is that it's able to identify, or it's more able, I guess you could say, has more of an ability. Realize it's 4:30, so give me 1 second. To identify clusters that are non-convex. Okay, so quick pause. I realize it's 4:30, so go ahead and check your emails. Okay, great. So both of the emails have in fact been sent out. So again, if you've been selected, please log off the Zoom room and go ahead and record your 10-minute video. And again, relax. Best of luck. It's not something super serious. As long as you can explain yourself and you meet all the specifications, should be good to go. Yeah, and if you haven't been selected, then we will basically wrap up with the final 20 minutes of class. Okay. Yeah, and again, if you run into any tech issues, you can email Jordan. He's there to help. Okay, I'll give it a couple more seconds just for people to check their emails. Someone said I didn't receive either email. Let me just, shouldn't happen, but let me just double check that. Check the list. Hmm. 1 second. Okay, I'm not sure. So basically, everybody that has just sent me a direct message saying that you didn't get an email, you've been selected. I'm not sure why you're not getting those emails. Let me just double check that. Okay, let me just send out that email again one more time. And if you've been selected, we can add on like an additional 2 minutes to the end of class. What is going on? Hold on 1 second. Record that. Okay. All right. Try this again. Okay, so I just sent out an email to the 12 people that have been selected. So for those of you who sent me a direct message, can you just verify that you got it this time? Got it. Okay. All right, cool. All right, so best of luck. And yeah, if there's any issues, email Jordan. He's there to help. And yeah, what we'll do is we'll wrap up with the remaining 20 minutes of class, and you can add on an additional like few minutes to submit a little bit late if you need to. Okay. All right. Where were we? Okie dokie. So, benefit of single linkage hierarchical agglomerative clustering is that it can, has more of an ability than the algorithms that we've seen before to identify clusters that are non-convex. In addition, it can also, or it has more of an ability to identify clusters that are of different sparsities. Also, those that have a different number of objects in them. Okay, so that's pretty cool. However, if we're particularly thinking about k-means, then there is an additional downside to using not just single linkage hierarchical agglomerative clustering in general, but basically using any hierarchical agglomerative clustering algorithm. And that you want to remember, for any hierarchical agglomerative clustering algorithm, in the beginning, we have to create a pairwise distance matrix between every pair of observations in the data set. So what that means is that that initial distance calculation actually increases the computational complexity of our algorithm, which basically makes us consider basically the set of observations and squaring them, whereas k-means doesn't necessarily do that. So I'll just say the computational complexity is higher than that of k-means. I'll say this applies to any standard foundational hierarchical agglomerative clustering algorithm, not just single linkage. All right, so those are some of the pros and cons of using single linkage for hierarchical agglomerative clustering. All right, any questions on that? All right, so let's think about another potential linkage function that we could use to measure the distance between two clusters in a given data set. So we already identified that single linkage is going to give us a problem. It's going to yield some issues when it comes to identifying these two main clusters here. So for instance, let's just say that we were at a particular iteration of a agglomerative hierarchical clustering algorithm. And we were at this particular iteration in which, let's just say, the set of observations circled here is one cluster. So this is, let's call this cluster one. Let's just say this green point is a singleton cluster. It's by itself. Let's call this cluster two. And then basically every other observation here is also a set of basically just a singleton cluster by itself. So this This is alone, this is alone, this is alone, this is alone, so on and so forth. So if we're using a single linkage to measure the distance between two clusters, single linkage is going to put that green cluster with this black cluster because they are closest, they're considered closest together. Oh, that's too funny. I've never seen that before. So we want to think about, yeah, like what kind of linkage function or what way to measure the distance between two clusters would basically make it such that the green cluster and this black cluster are actually considered further apart from each other than, let's just say, this green cluster, and let's call it this purple cluster here. So what way can we measure the distance between two clusters such that cluster 3 and cluster 2 are considered closer to each other than cluster 2 and cluster 1? I originally wanted to do a breakout room, but I think we're kind of running a little bit low on time because of the snafu. Any thoughts? So single linkage was measuring the distance between two clusters based on the two closest points. So we're going to introduce complete linkage, which is the opposite of single linkage, in which we define the distance between two clusters as the proximity between the two furthest away points in the two clusters. So if we define cluster proximity this way, then basically the distance between cluster 2 and cluster 1 is going to be something like this. They're very far away, the two furthest away points. On the other hand, the distance between cluster 2 and cluster 3, well, it's still just those 2 points by themselves. So the distance between the two furthest away points in those two singleton clusters are simply just those 2 points themselves. So we say with complete linkage, cluster 1 and cluster 2 are very far away from each other. And cluster 2 and cluster 3 are considered closer. Okay, so any questions on that? All right, so let's go through this same analysis again, clustering this data set, but now we're going to be using complete linkage to measure the distance between two clusters. So we start again by creating our proximity matrix of all observations in the data set, which represents also the initial proximity between all singleton clusters in the data set. Okay. And so the first step of the first iteration is to take a look at this first proximity matrix of clusters and determine what two clusters should be joined first. So what are the two closest clusters based on what this proximity matrix says? Yep, exactly. So technically you could have chosen 1, 2 to merge, or you could have chosen 3, 4 to merge. So let's just say we selected an arbitrary tiebreaker rule that had 3 and 4 merging together at this closest cluster distance. So the first iteration, we say that we're going to, again, merge cluster 3 and 4 at proximity 1.12. Okay. All right. So 3 and 4 merge together. And so next we need to update our proximity matrix. Now, technically, the proximity matrix is a symmetric matrix. So in theory, you can basically update both sides. But to save time, I'm only going to update the top right portion of this. Okay. I'm just going to ignore the bottom portion because I don't really, it's redundant information. So next, I update my proximity matrix of clusters now using the complete linkage way of measuring the distance between two clusters. So 0 and 1, that's the same as before. It's simply just those 2 points by themselves. 0 and 2, that's the same. So that's 4.27. And then 1 and 2, that's the same. So that's still 1.12. It's not going to work. Okay. And so next we need to figure out the the distance between cluster 0 and cluster 3, 4. Now in this case, the way that we're measuring the distance between clusters is not based on the closest set of points, but the 2 furthest apart points in those 2 clusters. So that would be 0 and 4 at a largest distance of 4.12. So the distance between 0 and 3, 4 is now 4.12. Okay. And the distance between cluster 1 and 3, 4 is now going to be the distance between the 2 furthest away points in those 2 clusters. So that's now going to be 1 and 4 at a distance of 5. So that's that distance. Okay. And finally, the distance between 3, 4 and 2 is going to be the distance between the 2 furthest apart points in those 2 clusters. So that's going to be observation 2 and 4 at a distance of 3.91. So that is the distance between those 2 clusters. Okay, that's the end of the first iteration. And so start the next iteration. So based on this updated proximity matrix of clusters, what 2 clusters would merge next? Yep, 1 and 2. So we would merge 1 and 2 also at a proximity of 1.12, because based on this proximity matrix, 1 and 2 are in fact the closest. So 1 and 2 are going to merge together. And so next in the iteration, we update our proximity matrix accordingly. And I'm just going to focus on the top portion. Okay. So let's see, 0 and 3, 4. We've already calculated that, so we don't need to do it again. Okay. But what we want to do next is calculate the distance between cluster 0, and cluster 1, 2. Okay, so in this case, we would find the distance between the 2 farthest away points. So that would be observation 0 and observation 1. at a furthest away distance of 5.1. So the distance between these two clusters would also be 5.1. Okay. And we'd also want to calculate the distance between cluster 1, 2 and cluster 3, 4. So that would involve finding the distance between the two furthest away points in those two clusters. So that's 1 and 4 with a distance of 5. So the distance between those two clusters would be 5. Okay. And so that concludes that iteration. So the next step is take a look at this proximity matrix and figure out what two clusters are going to merge together next. So what are the two closest clusters now based on this proximity matrix? So you want to scan the proximity matrix, look for the smallest distance, right? So we can see that 4.12, yep, is the smallest distance between clusters. So we merge cluster 0 and cluster 1, excuse me, cluster 3, 4 at proximity of 4.12. Okay, time. Those two clusters will merge together. Okay. And so need to update our final proximity matrix. So we have 0, oops, sorry, my bad, it's wrong. Yeah, 0, 3, 4, and then 1, 2. So we have 0, 3, 4, and 1, 2. Okay. And so the distance between 0, 3, 4 and 1, 2 is going to be the two furthest away points in those two clusters here. So that would be object 0 and object 1. So that would be, excuse me, the proximity, excuse me, of those two clusters. Okay. And so last but not least, we only have two clusters left. So we merge them at their proximity. So we merge cluster 0, 3, 4 and 1 and 2 at proximity 5.10. Okay. And so what that leaves us with is the clustering where they're all together. And I know I've ran out of time, so basically last but not least, let me just quickly construct the dendrogram. Again, on the y-axis, we have the proximity of the merge. On the x-axis, we put our observations. Okay. So 3 and 4 merge at 1.12. 1 and 2 merge at 1.12. 0 and 3, 4 merge at 4.12. And then 0, 3, 4 and 1 and 2 merge at 5.1. Okay, and this is my complete linkage dendrogram. Okay, done. Cool. All right, so that is the way to create a dendrogram using the complete linkage way of measuring the distance between two clusters. Okay, so I've definitely gone over, so I will stop there. Thanks for sticking around. I will stop recording.